This should be the last video for this midterm review. And before I start working out some of these problems, I would just give you a heads up that these are actually problems that were left out of the original review and have been added at the end. So they aren't necessarily in the order that you went through the class, but there are 4 or 5 of these problems that we've already covered previously. But I wanted to go ahead and still go through them and work out these problems because you may see problems like this on the exam. So we're actually ready for problem 32. And let me just put the problem up here from the review. Now this is actually a problem sort of where we left off. So this first one is sort of where we've been. Even up here you can see I made a note to myself that I needed to make a video. But anyway, so here's a function. F of x, capital F of x, is 1 over x minus 9 quantity squared. And then looks like there's going to be maybe 3 parts of the problem. We're going to graph it, figure out domain and range, and asymptotes. Now it's interesting, when you talk about graphing, when you have an online test, I'm very much of the opinion that whenever you solve a problem, you do what you need to do to solve the problem. So it's one thing you notice here, they give you 4 potential graphs as the actual graph of this function. That's very different than if you were just given this function and asked to create the graph. So on this problem, my attitude is I like to do things as simple as possible. So I'm going to look at this equation and look at these graphs and try and find something unique about this equation, and I can figure out which of these graphs is true, or at least which graphs I can eliminate. And the most obvious thing is, you notice we have a variable in the denominator, and we've learned that variables in the denominator usually cause us to have vertical asymptotes, and those vertical asymptotes are created by looking at what values of x would cause the denominator to be 0. In other words, what we cannot allow to happen is for the denominator of a fraction to ever be 0. So when we have variables in the denominator, we go look and we try to figure out what numbers the variable cannot be, right? We've talked about this before. So x minus 9 quantity squared, I've got to make sure x never equals 9. X can never equal 9. And when you get ready to graph that, this fact causes us to have a vertical asymptote at x equals 9. So it's going to be a vertical asymptotes are usually dashed lines. And remember, asymptotes are the lines the graph cannot cross or touch. Now these graphs aren't the easiest to see because they're pretty small. But I can right now go in and see which of these graphs has a vertical asymptote at x equals 9. This one right here looks like it has a vertical asymptote at x equals 0. This one looks like it's over here at maybe x equals minus 9. C looks like it has one at x equals 9. And then D looks like it has an asymptote at x equals 0. In other words, to solve this problem, all I did was figure out which graph has the correct asymptote, and there's only one possibility. And I've basically solved the problem. So like I said, on the test, there's no reason to, because look at the instructions. Graph the rational function using transformations. In the book, they always like you to graph using transformations. But basically, it's like, why am I going to knock myself out trying to create a graph when I can just look at these 4 possibilities and pretty quickly narrow down which one's correct? So sometimes, especially when you're trying to do graphing online, it just gets a little crazy, and it's not quite like the same if you were actually taking a paper test where you were actually asked to create the graph or to sketch the graph. Let me sort of cover up some of these answers so you don't see them. What's the domain of the function? Select the correct function below. If necessary, fill the answer box. So I should have been more careful because I don't want you to see these answers. There are 4 answers. Let's not even look at the answers. Let's just talk about what the domain is. And actually, the next question is the range. Let's just look at these graphs, actually the correct graph, and talk about domain and range. Sometimes we're asked to find the domain and the range, mainly the domain, when you're given an equation, and we've gone over that before. Other times you're asked to find the domain and the range when you're given a graph. And actually, the domain and range of graphs is actually pretty straightforward. All you have to do is, once again, the domain, I like to think of as all the possible values of x. So for this case, I know my graph looks like this. I'm asking myself, where does this graph, for what values of x does this graph exist? In other words, this may be hard to see, but for instance, when x is 0, does the graph exist when x is 0? Yeah, right? There's a point on the graph where x is 0. How about when x is 1? Now it's hard to see here, but this graph is actually going right almost on top of the x-axis. There is a graph here. So you can see here minus 20, minus 10, minus 5, minus 1, 1, 5. All these numbers in here, all these values of x, the graph exists. That means it's part of the domain. Once again, even in graphing, a good question to ask is, are there any values of x where the graph does not exist? And actually, there is. And it goes back to this vertical asymptote. And remember, the vertical asymptote is a result of this x minus 9 being in the denominator. So for the domain, when x is 9, the domain does not exist there. X cannot equal 9. If x equals 9, the denominator is 0, and you can see the asymptote here at x equals 9, and the line never crosses or touches the value of 9. That means the graph, the function, does not exist when x is 9. Now when you get larger than 9, numbers greater than 9, the graph exists. Numbers greater or less than 9, the graph exists. It's only when x is 9 that the graph does not exist. So therefore, in one way, we can say the domain would be all real numbers except x equals 9. And as it turns out, when we look at our choices here, that's what the correct answer is. The domain, this is where they write it in math language, x such that x is a real number and x cannot equal 9. So this is a fancy math way of saying x can be all real numbers except 9. How about the range? So the range is all the possible values of y. So now we're looking at values of y. Where does the graph exist? Or for what values of y does the graph exist? Let's start down here at the bottom. If I have negative values of y, is there a graph here any place? Does a graph exist? It actually does not. Matter of fact, the graph doesn't start until we get into the positive numbers, the positive values of y. As a matter of fact, there's actually a horizontal asymptote we're going to talk about in a minute. We've talked about the vertical asymptote. There's also a horizontal asymptote. It's sort of hard to see because this graph is just so small. This graph really goes like this, and then it starts to track the x-axis. So there's really a, whoops. Y equals 0 is the horizontal asymptote. And just to make it clear, up here when we were discussing the vertical asymptote, I was making the point that by looking at the equation, x cannot equal 9, and therefore that causes us to have vertical asymptote. If you're asked for the equation of the asymptote, you actually treat it like the equation of a line. So you would say the asymptote is x equals 9. The vertical asymptote is the line x equals 9. Horizontal asymptote is the line y equals 0. Now the graph doesn't exist where these lines are, but these are the actual asymptotes. So therefore now, the current question is what's the range of this function? You notice there's no graph below the x-axis. So the function is never negative. The graph only exists for positive values. The function is always positive. If we look at this graph here, y, the graph is always a positive y. So what do we say about the range? The range is when we could say the function is greater than 0, right? All the positive numbers. All these values up here is where the graph exists. Once you go negative, there's no graph here. So in the third part, when we look at the actual answer they give, the range of the given function is y is greater than 0. So they do it in, just like I did, in inequality. I called it f of x. They called it y, but of course f of x and y are the same thing. So once again, ranges and domains, when you're looking at a graph, are pretty easy. You ask yourself, for the domain, for what values of x does the graph exist, or is there a graph? Then for range, you ask yourself, for what values of y is there a graph, or does the graph exist? And then the last part, C, what are the vertical asymptotes? And then I think later on, that's for horizontal. We've already covered that. We said there's one vertical asymptote, x equals 9, and the horizontal asymptote is y equals 0. And those are the correct answers. All right, so that one's not too bad. And just so you know, the very last question of that previous problem, they ask about oblique asymptotes. And of course, oblique asymptotes are the asymptotes where it's at an angle. And we don't have one of those in this problem. Let me try and cover up this answer. 33, okay, now we're going back in time. We're going to pick up a problem that we didn't do in the initial review, but I want to go ahead and include it in this review. Write the expression in the standard a plus bi. So now we're back to the complex numbers, right? And here's an expression 4 minus I over 4 plus I. It's one of those sort of math rules that have been around for a long time. They don't really like, first of all, they don't like i's in the denominator, sort of like square roots. They don't like square roots or radicals in the denominator. And secondly, complex numbers, they always keep wanting us to put it in this form, the real part plus the imaginary part. So I need to do something to get this I out of the denominator. So let me go ahead and just write this problem down and we'll talk about it. So 4 minus I over 4 plus I. So this is going to be problem 33 in your review. So here's the expression. Basically my job is to get rid of that I, that imaginary number in the denominator. And there's a very simple sort of rule. You can call it a trick or a shortcut if you want. What you do is, now this is a case where we have a binomial. We have two terms, right? And these are added together. What you do is, turns out if you multiply by the conjugate of this first parenthesis. Conjugate means same two terms, except you change the sign in between. And you're going to see in a minute why this helps us out. But when you have like a binomial in the denominator with a complex number, the way you can get rid of the i's, it's multiplied by the conjugate. Of course, I can't just multiply the bottom by the conjugate and have everything be okay. I'm going to have to multiply the top by the conjugate also. So you notice this right here is a fraction equaling 1. So we haven't really changed the actual value of this expression. We're just going to change what it looks like. Now let me initially FOIL this, although in a minute I will also share with you a shortcut that I use all the time. This is really, if you look at it, it's really the opposite of the difference of squares. What do I mean by that? What if I'd given you a problem like that and asked you to factor it? You realized 4 squared 16, I squared is I squared. And you could have factored it. Well, that's actually what we have here. We're just going backwards. We're starting with this and ending up with this. So you can FOIL it. 4 times 4 is 16. 4 times negative I is negative 4i. I times 4 is plus 4i. I times negative I is negative I squared. So I've FOILed it. Or, you know what you can do? Because we know we are multiplying two differences of squares, the shortcut says you take the first term and you square it. In between is always a subtract, and then you take it the second term and you square it. Because if I finish this out here, negative 4i plus 4i cancel out. I'm left with 16 minus I squared. So it's up to you. If you want to FOIL it, fine. If you want to use a shortcut, the shortcut to me is pretty easy. I use it all the time. Now I definitely have to FOIL out the top. So it's going to be 16 minus 4i minus 4i plus I squared. 16 minus 8i plus I squared. Now you got to remember I squared we can replace with -1. So if I take this 16 minus 8i plus -1, that's the numerator. The denominator is 16 minus a -1. 16 minus 1 is 15 minus 8i. 16 minus a -1 is the same as 16 plus 1. Now, I've accomplished my first goal. The I is not in the denominator anymore. But you notice, and they do this in complex numbers, you know what they do? They want you to write it in A plus BI. A is what we call the real part. B is what we call the imaginary part. Right now, they're grouped together. It's pretty simple in this case to put it in the form A plus BI. We simply break up the fraction, and that is actually the answer. So the key is, once again, you have a complex number, it's part of a binomial, it's in the denominator, you get rid of it, you multiply top and the bottom by the conjugate. You can follow the shortcut and go from there and just do a little bit of algebra. All right, here's what I'm going to do. I'm going to get ready for 34, but I'll go ahead and well, let's do one more. Let's just finish this one out. I'll just start with a new sheet of paper. 34 says find the real solutions of the following equations. This goes way back where we're trying to solve equations. But in this case, our initial problem has a square root in it. There's my x. Another x. And the point of this problem is to solve for x. So I got a couple of things going on. My goal is to try and get x by itself on one side, which I do already have x over here, but the problem is I've got another x and it's sort of stuck under the square root. This x that's stuck under the square root is the one that's going to give me trouble, because somehow I have to get it outside of the square root to be able to try and solve it. So what I really need to do is to get rid of this square root. So do you remember what we do if we need to get rid of a square root? Right, we can square it. But what I need to do is I need to just square the actual square root. Right now, I've got 3 plus the square root. If I squared this side, it would be like a binomial. I would have to FOIL it. I don't want that. So what do? I really need to, first of all, get the square root by itself on one side. So my initial goal is just to get rid of the square root and create as few problems as possible when I try and get rid of the square root. So now that I've got the square root by itself on one side, how do we get rid of a square root? We square it. So the squaring cancels out the square root. But of course, in the world of math, if I want to square one side of this equation, I also have to square the other side. So the left-hand side is pretty straightforward. I now have 5x minus 1. The right-hand side, in case you guys forget, x minus 3 times x minus 3. All right? So if you FOIL this, you get x squared minus 6x plus 9. So now I have what we call a quadratic equation. Quadratic equation means the variable is squared. That's the largest variable. The way we solve a quadratic is to get everything on one side, and maybe we can factor, maybe we have to use the quadratic equation. So I'm going to subtract 5x and add 1 to get everything on the right hand side. So x squared. If I subtract 5x, here I have minus 6x, so it's minus 11x. I add 1. So there's the equation I have to try and solve. Fortunately, this, I believe, factors. I'm looking for two numbers that multiplied together equal 10, but when I add them, they equal negative 11. How about negative 1 and negative 10, right? When you multiply them, negative 1 times negative 10 is 10, positive 10. But when you add them, you get negative 11. And since there's no variable in front of my squared term, I can right away solve it. And now, solutions would be 1 and 10. Now here's what students always forget. Whenever you start out a problem with a radical, when you get your solutions, you feel like you're done, but you're not done yet. In the past, you were taught to check your work, but it was sort of optional. This is not optional now. Both these solutions might not work, so I got to check them out one at a time, which means I take 1, x equals 1, and I plug it in, and I see if it seems to work. So when x is 1, I have 5 minus 1, which is 4. Square root of 4 is 2. 3 plus 2, let's just do it. 5 times 1 minus 5. Five minus 5 is 0. I'm saying this has to equal 1, right? Because I put 1 in for the x here. This whole thing is 0. 3 plus 0 equals 1. Basically, it's saying, is 3 equal 1? No. So therefore, actually 1, even though I did the math correctly, it's actually not a solution. Let's go see about 10. Let me do it down here. 3 plus square root of 5 times 10 minus 1 equals 10. Is this equation true? 5 times 10 is 50. 50 minus 1 is 49. Square root of 49 is 7. Does 3 plus 7 equal 10? Yes, it does. Turns out we have one solution. All right. Not too bad, hopefully. Two problems left. The next problem is what's called piecewise functions, and then another graphing problem. Let me just go and stop now, because especially piecewise functions might take a little bit of time to explain. So let's stop now. Then I guess we'll have one more video for the last two problems.